Next up, we have Hans Utz of NASA Ames presenting on the Rover flight software for the VIPER mission. Hans, it's all yours.
Thank you very much. Yes, I'm Hans Utz. I'm the Rover software lead of the VIPER mission, and I created this talk together with Lorenzo Flütiger, who's the architect of the Rover flight software. Next slide, please. Quick outline of my talk. I'll start with a brief overview of the mission, and then introduce the Rover VIPER Rover software architecture and the three components: the Rover flight software, the Rover ground software, and the Rover simulations. Time permitting, then I'll go into the Rover software development a bit before closing out the status. Next slide. Looking at the VIPER mission, just to look at the unique configurations that create the challenges and provide the opportunities that the Rover software tries to answer. Next slide. VIPER is a mission to the lunar South Pole, a service mission, a robotic service mission, and in the upper right corner you see a picture of the lunar South Pole, and about 140 kilometers from there is the target area for the VIPER mission, the Nobile region, it's called. The prime interest of this mission are the areas marked red in the lower picture. These are permanently shadowed regions, which, due to the orbital configuration of the Moon, Earth, Sun system, have been in sun shadow for a couple of thousand years, if not far longer, and they work as cold traps, trapping volatiles, and that's where surface or subsurface or near subsurface water is expected by lunar scientists. As the rover, as the time delay to the moon is bearable, the rover is operated in continuous communication from Earth, and during out of comm, times of no comm, so when the Earth is below the horizon, the rover is merely exercising survival functionalities. The direct-to-Earth communication makes for a fast-paced operations concept, which is also important as the rover is essentially chasing the sun around the pole as it needs to charge its solar panels to survive, to charge batteries, to go into the permanent shadowed regions, and also to have enough battery power to survive the lunar nights. Next slide. The mission itself is a rather short duration mission, about 100 days, due to the fact that when the lunar summer ends, the nights get too long for the rover to survive on its batteries. So it has a firm mission endpoint. But we also have a significant mobility need. According to the scientists, we need to travel around 27 kilometers to answer the majority of their questions, or all of their questions that they put into this mission. The mission is also on a rather tight schedule, so we have about 3.5 years, if I'm counted correctly, from start to launch. Next slide. And this is the rover that was designed to do this job. The solar panels are mounted on the sides due to the low sun angle on the horizon, and a radiator is on top. It has a four-wheel drive system with an active suspension. Has a mast with a stereo camera pair and lights, as well as a directional antenna for communication back to Earth. The science instruments are 3 spectrometers and a drill, of which you see here the drill tower in the middle of the rover. Next slide. Yeah, short time comparison. Size comparison. Yeah, the VIPER rovers on the lower right here. It's somewhere in size between the Lunokhod rover and the U2 rover, currently visited the moon. Slightly bigger than the Mars exploration rovers, and significantly smaller than the Mars Science Laboratory or the Mars 2020 rover. Next slide. Yeah, so rover's relatively heavy, communicates over X-band, has the dimensions of a kind of a golf cart. As said, there's terrainability is a significant concern, given the lunar regolith, which makes gliding difficult with a lot of slip. So there's a that influenced the choice of the mobility system and the active suspension system to allow it to adjust center of gravity when going up or down slopes. The top speed being about 20 centimeters, not too fast. The primary the primary mobility mode is position control, not rate control. You can do that on the moon. That's what the Lunokhod rovers did, but that's incredibly stressful for operators. And the primary sensor modality is stereo camera assistance. Next slide. Yep, this is the instruments that the rover is carrying. There's mostly a reminder that the mission objective is not to build a really cool robot, but that we are chauffeuring the science payload. These 3 spectrometers and the drill that is gives us subsurface access. Yes, and with these answering to these to this unique mission configuration, we came up with our software architecture. The next slide, please. So the software VIPER rover software architecture is a split architecture. So we realized the opportunity of the low time delay and the continuous come during operations to reduce significantly the scope of the onboard software in complexity and reduce the effort as well as the computational requirements. And at the same time, we put a lot of robotics capability in the rover ground software, not to be confused with the ground data systems. So this is software that would typically reside on a autonomous mobile robot on board. Doing it this way allowed us to add robotic capabilities to the mission that would be really difficult to realize in onboard software at the time, at the speed, at the time available, at the budget available. The third component not shown here is the rover simulations, which would replace that surface segment up here in the upper right corner when hardware, when not running on hardware. Next slide. So first, let's take a look at the rover flight software in a bit more detail. Next slide. Yes. Here we're paying tribute to the aggressive schedule challenge. So it's based on the CFE CFS middleware, which is written in C, but all our applications are written in C++. As we wanted to use a more expressive and capable programming language to increase the development efficiency. The schedule constraints are also reflected in the choice of the target on the compute platform. So we're running on 2 computers, a radiation hard main processor, RAD 750, and a radiation tolerant, radiation hard is a radiation tolerant coprocessor for computationally expensive tasks, like image processing or image compression. So all of our imaging system runs on the code processor. You could probably push a lot of those functions into FPGAs, but that typically takes more time and effort. So we chose this architecture instead, and we chose VxWorks as the operating system mostly because there is no commercially supported Linux tool, Linux distribution for 32-bit Power PCs around that I know. Next slide. Going with the CFE CFS middleware gave us a lot of existing flight software and general purpose applications for managing spaceflight, which is great. It being written in C, comes the C interfaces, which are not very strongly typed as C and are often a bit cumbersome and error prone. So we decided to invest here in a bit of infrastructure for our mission and created a small C++ framework to wrap the CFE CFS middleware. All its core services, the lifecycle service, the publish subscribe architecture, the configuration parameter management service, and the logging capabilities. And we put that into an event-based programming model that's very similar to what you would know from the Boost ASIO library or from your ROS function pointer callbacks. It's strongly typed C++ template interfaces and provides basically the multiplexing of multiple event sources. So the software bus messages, so the publish subscribe messages from the architecture, the table updates, but also the I/O, the communication with the devices. It also has hooks for common CFS functions like the housekeeping telemetry requests or the application state model. And we added in the device communication, providing half async patterns, realized where writes are synchronous and reading is done asynchronous via multiplexed via the select calls. Next slide. We put a lot of emphasis on our interface definitions, so that's where things get interesting. As CFE surprisingly does not provide its own IDL, we chose the interface definition language that the ground data systems use, the Ames package that's used in ground data systems. We went a bit further than usual in not only specifying the ground to rover interface, flight software interface in those IDL, but also the flight software to hardware interfaces, which on the one hand makes for a bit more strictly typed hardware processing model, but also allowed us to reuse those for our robot simulations, which implementing these interface definitions on the simulation side. And as we tried hard to create single sources of information for all the interfaces, that resulted in quite a few scripts and generative processes upfront to generate the interface definitions partially directly from ICTs. Next slide. Looking at the rover ground software. Next slide. Here we are realizing the opportunity to provide robotic features that could not be easily done on board. This is based on the ROS2 platform and is deployed on the ground. We're tapping in here in the large ecosystem of open source robotic software and extending it with specific mission-specific functions and algorithms. This year, the architecture basically resembles a typical mobility system of an autonomous mobile robot, even though VIPER is not really an autonomous mobile robot. But you have the localization system, which provides the proprioception. You have the map generation box here on the lower right for the perception, and this feeding into the path planning and motion prediction modules on the right, which then feed into the green boxes of the ground data systems for operating the robot. Next slide. And the main modality is stereo point clouds. That's what's used for augmenting the onboard rover pose with visual odometry for rather precise relative pose estimation. So you see the picture here, wedges of the stereo point clouds coming from the rover in different colors, and they can then align to get a precise motion of the rover between those stereo point clouds. It's also used for mapping and terrain analysis, so creating 3D models of the terrain for providing visuals for robot operators, and also doing terrain analysis. So here in this picture on the right, identifying craters in the terrain that then can be used, feeding its obstacles into the path planning, where we do local path planning to create paths that align with the overall traverse path of the mission. As autonomy is hard to validate and verify, and takes time to get trust into, we chose the trick that all automotive companies do these days in providing their autonomous driving capabilities. We created an advanced driver assist system, so we're not directly sending the commands to the robot, but rather provide them to the human operators that use their human judgment and expertise to judge whether these are good motions to do, and then sending those or slightly altered ones to the robot, but hopefully significantly lowering their cognitive load while operating the robot, reducing their stress. Next slide. The third component of the rover software architecture is the simulation, and that's addresses the challenge of the testability of the lunar rover. On the one hand, hardware is always a contested resource and usually late, but also the sixth gravity that we have on the moon makes testing on lunar on Earth with relevant models difficult. A bit more about that later. We invested in a big simulation capability, which is based on the Gazebo simulator, which is a popular robotic simulator. Rover RSim is realized as an ensemble of plugins. So we modeled the rover, the lunar terrain, the lunar visual environment in great detail, high fidelity, as the simulation is also used for operations training and testing, and model all the rover sensors and actuators, and also provide means for fault injection, as a lot of our hardware faults are difficult to test with actual hardware, or the anticipated fault at least. Next slide. RSim is really tightly integrated with the rover flight software. We're realizing a fly as you test and test as you fly a paradigm here, where the devices are modeled at the protocol level and connected via virtual serial ports, UDP or SOCAT, so that pretty much an unmodified flight software is running both the hardware vehicles and as well as the simulation component. RSim. Okay, next slide. Our software development. We support multiple platforms. So we started with Linux, as that gave us easy access, and so that developers can directly develop on their own laptops. and then added a software emulation of the flight forward processor and operating system and compiler toolchain that's still available on every developer's laptop. And in parallel started with the software development units, reusing hardware from previous missions. Thank you, Laddie mission. So that we are hitting the ground running for when engineering development units show up for requirement verifications, etc. So on the top right, we have a picture of our benchtop setup, and the lower right is one of our terrestrial stand-in rovers, McGrew rovers they're called, for mass equivalent rovers. It's egressing a lander mock-up here. You see that it's stripped down to the bare minimum parts because it can only weigh 1/6 of the weight that the rover would actually weigh in flight. So it's a bit limited what you can do with respect to full integrated hardware testing. Next slide. We're also trying to answer to the schedule challenge in our development processes. As the mission itself follows a waterfall model, we're fitting in an agile development model into this by implementing the flight software in 7 builds, which start with build spec and end with acceptance testing. But within these builds, do an agile development on the 2-week sprints and concluding in project open show and tells that also allow us to provide early access releases to customers in the project. And that's backed up through a strong DevOps environment, building sources and running all automated tests that we can come up with. Most importantly, the end-to-end tests using our RSIM. And next slide. This is basically where RSIM comes to full bear with the Rover software development. As we are emulating all devices at the protocol level and have a high fidelity lunar optical simulation, where you can do a lot of testing in RSIM. And this chain includes RSIM and Rover flight software and Rover ground software, but also the ground tools. And so these end-to-end scripts are actually Python scripts that are commanding the ground control, ground data system software to communicate with the rover and basically doing the full end-to-end chain.
2-minute warning, Hans.
Yes. You see two images from RSIM. The lower one is the full fidelity simulation, where you see the crescent Earth in the background and the sun in the upper right corner. The gazebo view, not the camera view, so you don't get the lens glare effects that otherwise would make this picture very, very difficult to read. When you're a developer on a small laptop running in a VM, and not interested in the visuals, you can run similar to the upper right corner, where I have a plywood world with a plywood crater driving a McGrew model of the rover over the terrain. Next slide. As of status, we are at build 6 of the 7 builds that I mentioned. We are aiming to be feature complete with this build. We are about 1 year from software delivery and less than 2 years from launch. Next slide. And with that, thank you very much. And is there time left for any questions?
Yep. Have time for one brief question. What is the most complex piece of software that will be executed on the rover? Since the localization and mapping are done in the ground segment, what is the purpose of having fairly fast for space applications, a coprocessor at about 1 gigahertz?
Well, the computational power there is needed for image processing. Basically, the bandwidth is limited. The downlink bandwidth is limited, and we need to get the data down. And so we need to do image processing that's needed to reduce the data size, right? So you can do lossless compression, but if you need to do lossful compression, then you don't want to have artifacts that affect stereo. So you would need to do a couple of things that pre-processing steps of stereo processing on board before you download the data. We don't do full stereo processing on the board. That's where the computational power goes.
Okay, great. And we're out of time. Thanks, Hans, very much. We'll move the rest of the Q&A over to Slack.